So it's a pleasure to have Niao He. She's now at ETH. She was before assistant professor in Urbana-Champaign in Illinois, and before that she was a PhD student at Georgia Tech, notably working at the Academy University. Her interests are, as you might have guessed, on optimization, but not only. She's very active in machine learning and interface between the two. She's done a lot of interesting work. This morning we discussed a bit about the recent work that are related to min-max problem and reinforcement learning specifically. And today I think she's going to talk about a bit what you've been doing in the reinforcement learning area. So it's a real pleasure to have you on the stage.
All right, thank you so much for the introduction, and indeed it's a great pleasure to be here, and also very excited to finally be giving an in-person seminar. If you have any questions, feel free to interact at any time. Okay, so as Lorenzo introduced, today I'm going to shed some light with some of the very popularly used reinforcement learning techniques, and discuss a bit what are these techniques, and when and how do they work in theory and also in practice. So let me get started. Okay, so before that, I want to maybe just give you a very brief introduction of what I work and also with my group. So in our group, which is called Optimization Data Decision Intelligence, we work a lot of the intersection between optimization and machine learning. And particularly, I think maybe all the audience here agrees with me that optimization and machine learning really plays the most central role in between this whole data to decision pipeline. And we know that given different appearances of the data, either those are streaming data, distributed data, or whether those are like static or dynamic, or they're noisy or adversarial, we can always find the good or some appropriate optimization or machine learning frameworks to handle them. And a lot of our work really focuses on how we can design principled, efficient, data-driven algorithms so that we can make not only efficient, but also robust and hopefully also intelligent decisions for many of the applications in machine learning. And in this talk, I will particularly focus on some of the recent work we have done at the intersection of optimization and reinforcement learning. And before that, I want to say this is really the very exciting and interesting crossroad of optimization and the reinforcement learning that we're standing at right now. So if you look at I think many of you are probably very familiar already with the history of optimization. And if you look at kind of these two very separate fields, and it's really interesting to see how they really come to a confluence in the recent years. So on the optimization side, we have seen a lot of transitions or evolutions from like solving linear programs to stochastic programs in the 1950s and all the way down to more general convex programs. And recently there was a surge of interest in stochastic optimization driven by large-scale machine learning problems. And more recently, I think there was really a lot of emphasis shift into non-convex optimization. On the other hand, in reinforcement learning, we have seen the evolution from the more classical dynamic programming and control tools to the interest of model-free control, where we don't really know the underlying dynamics of the systems, and to the recently the really excitement of a lot of breakthroughs in policy optimization, and also that leads to a lot of the success in deep reinforcement learning. And as you can see, that really optimization always takes one step ahead when you look at these two histories, right? A lot of these kind of linear programming perspectives, policy iteration really hinges upon like linear programming that was introduced by Danzig. And a lot of the model-free algorithms like Q-learning, TD learning, those are really just special cases of stochastic approximation that was introduced in optimization literature in the 1950s. And a lot of the recent advances, like in deep reinforcement learning, like a lot of the policy optimization algorithms are really just cases of like first order methods that was extensively studied in the optimization literature. And So in our group, and also what I'm very excited about and also talk about today is really at the intersection of non-convex optimization and deep reinforcement learning. So just to maybe to make sure everyone is on the same page, what is reinforcement learning? I guess many of you who have taken the machine learning course already know part of the story here. So in a classical reinforcement learning setting, really that we say an agent tries to learn to act or to make a sequential decision based on interacting with the environment, right? So this is kind of a dynamic environment where the agent at every iteration takes an action and it receives some state feedback from the environment. It also at the same time receives some reward signals from the environment and do this iteratively and tries to maximize what is going to be the long-term reward, right? In this case of this Super Mario agent, you can view that the actions he can take is basically either take up or down or left or right? So there are really just 4 different actions. And the environment here is like, you can view it was given by just this system here, that the reward is basically here, the scores that it will get, and the state is really represented by kind of the pixels of these whole images or the input. So an agent could also be like, say, a self-driving car, where here in this case, we really try to like reach from one destination to the other place as fast and as safe as possible, right? The controller here is really just to how you will control the steering wheels, and the state is given by basically kind of the whole the status of the agent, how closely to the cars nearby, and also what are the signals you get from the sensors, right? So these are kind of typical applications of reinforcement learning. And I guess I want to emphasize that reinforcement learning is fundamentally different from classical control or supervised learning, right? Because here, first of all, there is not really a supervisor here. So what you get is only some intermediate reward. And for any action you take, those action could influence not only just your intermediate reward, but also your future rewards, right? So there is really a delayed feedback comparing to what we typically see in a standard supervised learning setting. And then in different from control here, oftentimes we have an unknown environment. We don't really know what is the system transition models behind it. So that is essentially why we have to learn about those environment. And then different from supervised learning, also the underlying data that we collect by interacting with the environment is really not stationary, right? Those are not IID data, because those are data that corresponds to different policies we deploy, and also it corresponds to the Markov systems behind of this whole model. And so there are a lot of differences and also a lot of challenges comparing to supervised learning. So maybe I want to first give you just a brief introduction of the basic terminologies if you're not very familiar with of this. So oftentimes we focus on a mathematical model called Markov decision process, which consists of some state space S, action space A. Those could be finite state or could be continuous state or action spaces, and transition probabilities, which are corresponding to the probability that when you're at state S and taking action A, how likely you will transit to a new state S prime, right? And I'm going to denote mu as the initial distribution of how we're going to select this initial state S0, and some discount factor gamma between 0 and 1 that discount the total reward you will get. And there are 2 main kind of components of reinforcement learning, right? One is the policy pi that you will deploy. So this is here, in this case, I'm going to consider a stochastic policy, which is basically a mapping from your state space S to some probability space over your action space. And then another key component of reinforcement learning is the value functions, which characterizes how good your policies pi are, right? So this could be the value functions or the state value functions or state action value functions, which we'll introduce here. So for instance, here's the definition of the value functions of V of pi. That is basically to say, if you start with a state S at the beginning, what is the long-term reward you will get, right? This is the expected reward you will get. And other value function Q pi is basically if you start with state S and action A, what is going to be the long-term reward you get. So this basically characterizes how good is the state or the action you take. So this is one of the fundamental problems in reinforcement learning, which is called policy evaluation, is to say if you're given this policy pi, I want to try to evaluate what are those value functions. Okay, the ultimate goal in reinforcement learning is optimal control problem, which is to say you have a family or you have a policy class, you want to try to find out what is the best policy pi among all feasible policies that will give you the maximum return, right? You want to really maximize your value functions over pi. So it has been known that computing either this policy evaluation or these optimal control problems are equivalent to basically solving some Bellman equations, right? In the case of policy evaluation, this is equivalent to solving Bellman expectation equation, which basically says your value function V of pi or Q of pi are basically nothing but just fixed point to these Bellman operators, okay? And similarly, your optimal value functions and optimal Q functions are also just a fixed point to these Bellman optimality operators, right? So I'm not going into the details how those operators or those Bellman equations come from, but I want to highlight that most of the kind of classical reinforcement learning algorithms based on dynamic programming are essentially based on solving these Bellman equations. Okay. However, when we try to move to kind of the more modern reinforcement learning regimes, we see that the challenge is really that oftentimes in practice, the number of state space is super large. So for instance, if you think about the chess game, the number of states are of order of 10 to the power of 120, right? So that means it's impossible to store in your memory this whole vector V of pi or this value functions Q of pi, right? So memory-wise, this is just something impossible, and also computation-wise, this is also prohibitive. So the class of your policies in this case is, as you can think about this as a mapping from your state space to action space, which is also very huge. So another sort of challenge with reinforcement learning nowadays is really the data insufficiency problem that oftentimes, unlike simulated environment, we cannot generate as many data as we want, right? So there is a lack of data in most of the applications. And also oftentimes the data that we collected are based on some policies from past, like your past policies or your past strategies, which does not really align with the policy that you're interested in or the policies that you deploy. So there is also a notion of causal insufficiency here among the data. So that brings a lot of challenges, not only on the optimization side because of those large scale of the problem, but also on the generalization side, because we have to really deploy a lot of the function approximation techniques in order to generalize to different state and action, and also a lot of challenges with exploration. So despite these challenges, I would say like reinforcement learning has really received a lot of breakthroughs, particularly in the applications. We have seen a lot of really remarkable successes in playing different board games, video games, and also some simple like robotics experiments. And I think it's not too surprising that really behind many of these empirical successes is really that a lot of the recent algorithmic advances that people introduced, or sometimes I would rather call these engineering tricks, right? So there was the use of like neural networks pervasively in estimating those value functions or estimating a model. There was the use of like, say, for instance, experience replay, where we try to memorize data and try to reuse data more efficiently. There was also the use of, say, targeted networks, which are commonly used to really just to reduce so-called overestimation bias and trying to make your problem more like a supervised learning setting. And then there was lots of other techniques people use, right? So the combination of many of these tricks is really what leads to the great success of reinforcement learning in practice these days. And if you think about it, there is really a wide gap between the theory and practice. On the theory side, most of the classical literature or really focus on very small state action spaces, oftentimes just a finite state and finite actions, right? At the best, those literature talk about linear function approximation. And most of the theoretical results are for like very classical Vernina value-based or policy-based methods. And in the practical side, we almost always deal with very large state space and action space, sometimes even continuous. We use deep neural networks all the time. And the most of the practical algorithms, people add on top of it lots of different tricks and variations of it. And so there's really like a fundamental gap between the theory and practice. And one of the prominent, I think, example of this theoretical and practical gap is really that the so-called deadly triad dilemma. So in the theory side, it is well known that like simple algorithms like Q-learning, even if you use linear function approximation, this might diverge even for like very small toy MDP examples. On the other hand, in practice, people use Q-learning, combine it with very large neural networks, and it seems to perform super well and learns to play many of those Atari games very well. So what is really this missing piece here, right? Why is the deadly triad is suddenly not taking place in practice, right? What is it really because we're using larger networks that makes this divergence less likely to happen, or is it because of these other tricks people use that avoid this divergence? So in this talk, so I think that is really a long introduction. What we're really trying to show to discuss is trying to understand like what are the roles of these different RL tricks people use in practice, and what do we know about the theoretical guarantees, and hopefully we can bridge the theory a bit closer to the practice. So in this talk, I'm going to talk about these three particular tricks. The first one is the so-called double learning and also target networks. Second trick is the use of neural networks for function approximation in reinforcement learning. And third one is to use entropy regularization to kind of encourage exploration in practice. So are there any questions at this point? Okay, good. So maybe let's look at the first one, right? So as I said, like in practice, oftentimes because of the large scale of the state and action spaces, oftentimes we use either linear function approximation or neural networks. There are also many other ways you can do function approximation, right? You can use decision trees that Lorenzo was teaching today, and you can also use, say, kernel methods. You can use generative adversarial networks. You can use many ways to try to do function approximation here. So here, particularly, let's look at just the linear function approximation and neural networks. So if you think about, say, this very classical algorithm Q-learning, and if we use linear function approximation to estimate those Q functions, right, those are the state action value functions. So in the linear function approximation case, this is basically how the Q-learning algorithm performs, right? At every iteration, you update your parameter theta, right? Those are the weights of your linear function approximation there. And then you compute, first of all, this so-called temporal difference. This is basically the error of your Bellman equation at this sample sk, ak, and sk plus 1, right? And then you multiply this by the gradient of Q function, which is those feature mappings phi, right? So this is kind of the very classical Q-learning algorithm. If you use neural networks to parameterize your Q functions, right? Let's say you are using those weight matrices W, sigma are your, let's say, your activation functions, right? Here, our parameter theta is basically those W's, right? So every iteration, again, you basically update your parameter theta, right? By first of all computing this temporal difference, and then multiply it by the gradient of your function f. So this is kind of the main building block of the deep reinforcement learning algorithms based on deep Q network. So as you can see that in these updates, one of the kind of the well-known issue with Q-learning algorithm is the so-called maximization bias, because here we're using the same noisy function estimation f to not only to select the best actions at every iteration. So you can imagine that your f is too noisy, then choosing the best action based on this noisy estimator could cause positive bias here. Let me give you just an example here, right? Say, for instance, if you think about this very simple toy example where you have two state A and B and two termination states. Let's say at state A, you have you can take two actions, left or right. If you take a right action, you get 0 reward. If you take left action, you also get 0 reward. But this will lead to a new state B. And at this new state B, by taking different actions, you might get you can get some reward that follows this normal distribution with mean -0.1. As you can see that if you're at state A, then the best action you should choose is really to take this right action, right? Because that will lead you to 0 reward. But if you take the left action, that will lead you to, in expectation, a negative reward, right? However, if you run Q-learning algorithms, so basically there will always be cases where you might observe positive rewards by taking this left action from state B, right? And that tends to kind of make the algorithm in favor of always taking the left action at the very beginning. That's why if you look at this curve on this right figure here, this blue line, on the y-axis, here is the probability that you will take this left action. At the very beginning, the algorithm will strongly favor taking the left action because there was incentive to go left because you sometimes see the positive rewards there, right? And that is what's so-called the maximization bias or overestimation error in reinforcement learning, Q-learning algorithm particularly. And one of the fix of this algorithm is called the double Q-learning algorithm. This was introduced by Wan Hassett in 2010. And this was since then become kind of the main workhorse for deep reinforcement learning. So the idea here is instead of using the same Q functions to select the best action and evaluate it, we're going to maintain two different networks or two different Q function estimations. You use one function estimation of Q to select what is the best action, and then you use a different Q function estimator to evaluate how good is that action, right? So this is a very typical it's a very standard technique people use in statistical estimation to just to reduce this. Yes?
So here, the example was just one action chosen, right? From B, those are not branches that are taken through actions, but that's just the stochasticity of the reward.
Yes, yeah, these are just, there is just one action, but that action takes a random reward, follows from this normal distribution. Yes, yes.
Because you just said that this trick is quite standard in statistics. I don't recognize it.
So for instance, yeah, you want to maximize like if you have a bunch of distributions and then you want to find what is the maximum mean among those distributions. Okay. So of course, the easiest way is you just generate samples for each distribution, and then you just find out which distribution gives you the largest sample mean, okay, right? That of course is suboptimal. So the better way to do this is you generate a sample from each distribution, right? You find out what is the one that gives you the maximum sample mean, and then you regenerate some new samples to evaluate what is the sample mean at that distribution, right? So you use two separate samples to reduce this correlation. So that is basically the key idea here, right? To really avoid this correlation between picking the best action and evaluating that action. You want to use different estimations for it. And particularly in double Q learning, what they do is they maintain these two estimators and then they update them symmetrically, right? You're using this Q of theta A to estimate, uses this Q of, use one network to estimate the other parameter theta A, and then you do this symmetrically for the other network too, right? So that's why they have this name double Q learning. So as you can see in this particular example, this double Q learning actually seems to perform much better than Q learning algorithm. and it doesn't have this overestimation issue here. Right, so this is the algorithm that was extensively used in practice, and what we try to study here is really why does it work, and also to be more precise, does it really work? Does it really give you better convergence? Does it really give you something more robust than Q-learning, right? So to answer this question, right, so one way that we think about to make a fair comparison is trying to measure their convergence, not only just the convergence, but also their non-term, like their asymptotic variance of their parameter estimators, right? So we know that from central theorem, central limit theorem, if you have enough data, right, eventually your parameter will always converge to some theta star, let's say, right? And under nice kind of statistical assumptions, we can show that, right, this will actually converge to a normal distribution if you look at the difference between theta k and theta star. And this asymptotic variance sigma is kind of what determines essentially the stability of the algorithm, right? Like what is the variance in the end asymptotically. And this square root of k, which is basically is to some convergence rate, like 1 over square root of k, that determines how fast it converges. So in this case, we're trying to compare kind of what are the asymptotic mean square error of these two algorithms. And the asymptotic mean square error is nothing but just the trace of this asymptotic covariance sigma here. Okay, so we can define this for the Q-learning algorithm, right? What is the limit of k times the expectation of theta k minus theta star taken square? We can also define this for this double Q-learning algorithm for this parameter theta a or parameter theta b. We can also define it for the average of those two estimators, right? Just to, right, in the same way. So one of our main results is given here, right? So we tried to use the same step size for both of these two algorithms. I say the same, it's really the magnitude is the same. Both were using this decay in step size 1 over k. The difference is here for double Q-learning, we use twice the step size. And the reason for that is, maybe I didn't mention here, is like in this update here, what's typically done in practice is you randomly decide to whether you flip a coin and then you decide whether you want to update theta A or theta B. Okay, so here we use twice as large of the step size as Q-learning algorithm, because as you can see that here at every iteration, you're only updating part of the parameters. So by using twice as large a step size, we ensure that you're updating your parameters kind of in the same frequency as Q-learning algorithm. And this also guarantees that they have the same transit behaviors eventually. And assume both algorithms will converge, right? That then we shown that actually what turns out to be quite surprising to us is the asymptotic mean square error of this Q-learning algorithm. If you output either of those parameters, theta A or theta B, is actually worse than the asymptotic mean square error of Q-learning algorithm. Okay, so that says asymptotically this algorithm doesn't seem to be better than Q-learning. Okay, however, we've also shown that if we use the average of those two estimators A and B, then we've shown that the asymptotic mean square error is in fact the same, not too worse than, it's exactly the same as the asymptotic mean square error of Q-learning. Again, that basically suggests that asymptotically this algorithm seems to behave no worse or no better than Q-learning algorithm. This result is based on basically analyzing the Niao equations of the underlying stochastic approximation. Like the analysis is actually fairly straightforward. I can show it in one slide, but I'll probably skip it here. And we also run a number of experiments, and turns out this actually in applications that are not pathological, as what I showed before, we can show that exactly what we expected in theory, right? We can show that if you run both Q-learning and double Q-learning, let's say here in this example, Q-learning is this red curve, and double Q-learning is this blue curve. If you are using the same step size as Q-learning, then it actually converges slowly. However, if we use twice the large as the step size, which is going to be the the black line here, it actually has the same transient behaviors as Q-learning algorithm as we predicted in theory. And the asymptotic mean square error is actually worse than Q-learning algorithm. Q-learning algorithm is this red curve here. If we output the average of the two estimators, which now gives you the green curve, which aligns with Q-learning algorithm. Right. So similarly, if you use different settings using different rewards, it's always like this. So this is one example. We also try to say, for instance, grid word, something similar happens, right? If you use the same step size like in double Q-learning as Q-learning, it actually converges worse than Q-learning. But if you use twice the step size and further you output the average of those two estimators, you expect a similar behavior as Q-learning, sometimes slightly better. Okay. So basically, so of course you might be wondering then what happens with that overestimation bias example, right? In that example, we see clearly double Q-learning performs better than Q-learning. So this is, we also did the same example. It turns out that yes, indeed, in this case, there is this differentiation between these two, the behaviors with two algorithms. And in fact, here, even with, if you output the average of the two estimators, it actually performs still much better than if you just output either of those two estimators. So this is kind of the phenomenon that the theory was not able to prove, to justify. Because the theory, what we have is really just to say that asymptotically, double Q-learning should not be anything better than Q-learning. But in practice, at least in this example, somehow this is not aligned with the theory. And then what's interesting also is that if we, instead of using tabular setting where we represent just your Q functions for any state and actions, here let's use neural network function approximation for it. Then we've shown that in this case, actually, we don't really observe this overestimation bias issue anymore. And here in this case, again, this aligns very well with our theory that double Q-learning is not necessarily, is only better when you use like the twice as large as the step size and also using the average output. So this kind of leads to, again, the question that does neural network actually helps you, right, to avoid this overestimation bias? But this does not necessarily help you to have a faster convergence. I think that's kind of more or less the story here. Are there any questions at this point about the results? Yes?
What is the, if you are to plot some kind of indicator of how good your asymptotic approximation is, what M would be, like, did you study how large should M be in order for the trick not to work, or how small
That's an excellent question, and that's something remains unknown even in the case of Q-learning or any other like reinforcement learning algorithms in general. How large the neural network it needs to be in order for the algorithm to converge or in order for the algorithms to behave like reasonably. And that kind of leads to the second topic that I want to discuss is really trying to understand why using neural networks actually guarantees convergence and also why it actually works well, fine in practice, although this seems to be a black box, right, when you use neural networks. Okay. Particularly, I want to go with a very simple setting, right? Besides, before introducing all of these complications with double learning and all of those other things, let's just consider the very, very basic setting where you're given a policy pi and you want to evaluate how good it is, right? So this is called policy evaluation. And the simplest algorithm to do that is called TD learning. Right, so and here I'm going to even consider something even simpler. It's just this two-layer neural network. We have only one single hidden layer with m number of nodes, right? The neural network or the function approximation of this value function v is basically represented as the following, right? We're taking some linear functions, wi transpose x, right? We're adding this is a rectified linear unit activation function. I'm just using this plus sign here because I'm just taking the maximum of this and 0. Okay, and a bunch of weights alpha I here, coefficients alpha I. So this is just the simplest two-layer neural network you can think of. And here in particular, I'm going to just initialize those coefficients alpha I to be just this uniform distribution between -1 and 1. And those wi are the only parameters that I'm trying to learn. Okay, so alphas are fixed and w is only parameter that we're trying to learn here. And I'm going to also initialize those w as just normal Gaussian random variables. And so this is basically the TD learning algorithm, right? That's what I discussed also before. So at every iteration, you just update your weight matrices W by computing, first of all, what are the temporal difference, right? This is the error of your Bellman equations times the gradient over W. Okay. I should mention that this algorithm, you can sort of view it as an algorithm that solves this type of optimization problem, right? You want to minimize the mean squared Bellman error. Right, you want to, because we know that the optimal value function is a fixed point to this Bellman equation, right? So if you minimize mean squared error here, if the optimal solution, if you have some W, then make sure this is equal to 0, then that corresponding value function is going to be the optimal value function, right? In this case. So if you look at this objective here, and if you think about how we parameterize these value functions, this objective is not necessarily going to be convex, right? This is a non-convex objective because your V functions are, so you have this nonlinearity here in your value function estimation, right? If you, and I should also point out that the TD learning algorithm, like this algorithm that we write out here, this is not necessarily just a running gradient descent to solve this optimization problem. So this is oftentimes what we call stochastic semi-gradient, because this is not the true gradient. Okay, so the true gradient, so this is actually the gradient corresponding to a moving target, right? So basically you are replacing this every time by your most updated value function approximator, and then you solve this by stochastic gradient descent. So in some sense, there are a number of biases here when you try to solve this minimization problem from TD learning, right? So it's not necessarily the true stochastic gradient descent method here. There's a non-convex objective we're dealing with, right? Which does not always guarantee that you will be able to find the global optimal solution. And also there is a notion of function approximation error here, because those value functions, because your true value function is not always representable by this two-layer neural network, right? We write down here, right? So there was really a number of biases comes into the picture. And then the interesting question here is really that by solving this with TD learning algorithm, does this really guarantee that we will be able to find the true value function, right? Yes.
Confusing question.
Sure.
To minimize, so there will be two components. Right? One is how good the approximation is, and the other one is how close you are to the true fixed point.
Right.
Can you disembed these two components of the error? Is that something that you can do, or you hope that you have the approximation and not the fixed point?
Right, that's exactly what we're trying to do here, is really to decompose these two, right? What is the approximation error, and then what is the optimization error? Of course, even if we are able to handle the approximation error here, like again, the optimization error part by itself is a bit interesting to see that, because this is still non-convex, right? So the question that we're trying to ask here is, does this really lead you to the true value function? If so, then how large should be the neural network be? What is the number of nodes you need in order to control the approximation error side? And also, what is the number of iterations you need in order to converge to the true, in order to solve this problem, right? So this really corresponds to the optimization error and approximation error, as mentioned. Yeah. So I should also mention maybe some of the existing theory, right? Most of the existing theory only discuss the TD learning algorithm when you have linear function approximation. And there are some recent results in terms of what are the finite time analysis of these algorithms under different settings, like ID settings, Markovian settings, with or without projections. All these are fairly new results. Besides TD learning algorithm, if we look at the stochastic gradient descent algorithms in supervised learning settings, there are a number of recent results that talk about what are the convergence of stochastic gradient descent in the infinite width limit regimes or in the finite width limit regimes, right? But those are not necessarily, but as I said, the big challenge here is TD learning is not really stochastic gradient descent, right? So one of the key challenges in directly applying also many of these existing results that are oftentimes based on neural tangent kernels or over-parameterized neural network, the main challenge is really that many of the results there requires the number of neural networks to be polynomial in terms of the number of size of your data. Right, so in the TD learning setting or in reinforcement learning setting, this basically requires a massive amount of over-parameterization that are polynomial in terms of the state space. And this apparently is not suitable for TD learning or for reinforcement learning, because if you need polynomial size of your state space, why not just use tabular setting, right? So many of these existing analysis does not directly apply here. And another kind of key difference that doesn't really apply to TD learning setting is that many of the existing work on gradient descent requires these lazy training regimes that where your parameter actually does not drift too far away from your W, and you can actually control that by using more neural networks, by using larger neural networks. But in TD learning setting, somehow it's very hard to control this drift between your parameters. And in order to address those challenges, right, what we propose is really that we need some kind of regularization to be imposed to the TD learning algorithm in order to make sure it will work. So we introduced the two types of regularization techniques. The first one is called early stopping, right, which basically says you wanted to find a good time to stop your algorithm to avoid that your parameter drifts too far away. So you want to control your optimization error somehow and balance it with the statistical error. And then the second algorithm we propose is we introduce is the maximum regularization. So we basically explicitly added this maximum regularization that the weight parameters for every component is going to be very small, right, of order 1/√5. So that basically means at every iteration, we're going to do a projection onto this space here. And for this this other one, we don't do any projection. So we introduce these two regularization techniques, and here are the main results we show, right? So the result is as follows. If we assume the value function stays in some function space that was generated by the so-called neural tangent kernel, which I will not go into details here. But one thing I would like you to remember is that this neural tangent kernel space is indeed a dense space in terms of the in this whole continuous function space. If your domain is compact, that basically means that any kind of continuous function can be well estimated by this neural tangent kernel space. And so this is basically a very mild assumption here. So basically what we've shown is that as long as the number of samples that you use to run the algorithm and the network width is as much as these numbers that I give here, then you can show that this algorithm actually converges to the true value function V, despite the non-convexity of the objective, despite the function approximation going on, okay? And despite that, this fact that this is not even gradient descent. So the specific results are like the number of samples we need for this projection-free algorithm is of order 1/epsilon 6. And the network size we need is of order 1/epsilon 6 too, right? So this will depend also polynomially in terms of this parameter V bar. This V bar is nothing but just some RKHS norm of this true value function. So it really characterize what is the smoothness level of your value function, true value functions. This has nothing to do with your state space or your action space, right? And then with the maximum regularization, we're showing that the sample complexity drops to 1/epsilon 4 and the network width drops to 1/epsilon 2. Okay. Yes. Any questions? Okay.
Sure.
Yes.
Yeah, so couple. So one is so just this is probably because I'm not interpreting the results in a good way. So here, the smaller are the better, or something is getting worse.
So the smaller order, the better.
The smaller the R. It seems like there, what I want to do is just put R time. But presumably we place something somewhere else.
Right. Yeah.
Where?
So first of all, so these results require, first of all, your R to be at least as large as V bar.
Okay,
so right. So you cannot make an R arbitrarily small. Yeah.
The other one which I didn't miss is that. So you need the max norm. Why the max norm? And for example, if you put instead of the max norm, the Euclidean norm, you get back the ETH-6.
Let me get, yeah, you can use other norms, right, instead of this particular regularization. Let me get you to this maybe summary of the table. So there was existing work that used this L2 norm in this work by Zha et al. So they used the explicit L2 norm instead of max norm. And what their result shows that like the number of network widths is as large as 1/epsilon 8. This is how large the neural network needs to be in order to get an epsilon accuracy. And the sample complexity is 1/epsilon 4, the same as ours. So what we've shown here is if you use maximum regularization, you only need the 1/epsilon 2 number of neurons in the neural network representation. And this is really very tied to the fact that so this particular regularization is really very tied to the fact that is really something that really comes up from the analysis that we realize this is the only thing you need to control is just for each independent W, those has to be bounded. And then you can leverage a more tighter concentration bounds in order to reduce significantly the network width. And so the kind of the moral of the story here is really you need to impose some sort of regularization, and then only modest amount of overparameterization is needed, right? In order for you to learn the optimal value functions. There is of course a trade-off between like using projection or using regularization or using explicit regularization and implicit regularization. So for instance, here without doing any projection, if you use early stopping, then this does not restrict, put any restriction on your function approximation because we're not putting any restriction on W, right? So here you can explore the full power of neural networks, but it requires much, but it will converge much slowly, right? It will require more samples in the end because really you have to use a very small, tiny step size at every iteration to make sure your parameters doesn't explode, right? On the other extreme, if you use maximum regularization, as Lorenzo pointed out, right, we have to really impose this projection, this R on your neural networks. And this R basically will restrict your representation power of your function approximation. And then, but it will give you faster convergence. So there is really this trade-off between the convergence and also the representation power of the neural networks. And of course, what I've shown here is really just applying to, as you can see, that the result only applies to TD learning algorithm, two-layer neural network. Everything I discussed here can be easily extended. If you have multiple neural networks, you can use similar neural tangent kernel analysis to obtain similar results. And also, you can also obtain similar results not only for TD learning algorithm, but also for other algorithms like Q-learning etc. Right? So which I will not go into the details there. So with maybe I think I still have a few minutes. Let me maybe jump to the third trick, which is the so-called entropy regularization, and it has been pervasively used these days in policy optimization. And there are many algorithms, like if you look at the literature, that uses this notion of entropy regularization, more or less, in reinforcement learning. And there was a lot of questions about, like, what is really the role of entropy regularization, right? There were some kind of numerical evidence suggests that this will encourage you to have better exploration, right? Because you are making your policy more stochastic. There are also results that's trying to hint that this will give you better landscape of the objective and will lead to faster convergence. Right, so in this work, we try to really understand the role of entropy regularization, particularly in the function approximation regime. Most of previous work really focused on the tabular settings. Here, what I mean by function approximation case is really where you directly look at your objective here, where you want to find the best parameter theta. The theta is the parameter of your policies. So you're parameterizing your policies into with this parameter theta. Right, and then you just want to find out what is best theta. Okay, so this is kind of the goal of policy optimization, and this in general is a heavily non-convex objective. And particularly, we're looking at these softmax parameterizations, right? So where you're just taking the softmax of some linear function approximation or some neural networks here. Okay. So there are two types of algorithms people typically use in practice. One is called policy gradient, which is just a gradient ascent, right? You just compute what is the gradient at parameter theta, and then you update it, right? And what do I mean by entropy regularized object policy gradient is basically to say in your objective, you add this entropy term, right? Which is basically the expectation of your negative log of pi. Right, you add this term into objective, as you can see that if this parameter lambda goes to infinity, actually this should be max, not minimum. If this lambda is going to infinity, then that means the optimal policy here should be just the uniform policy. Okay? Here, basically, the larger lambda is, then you are encouraging more kind of stochasticity in your policy pi. So policy gradient is just performing one step of gradient ascent, right? And the natural policy gradient is another algorithm that was more, is kind of one of the building block of many of the recent successes in deep reinforcement learning algorithms, is to really leverage the feature information matrix and also the underlying curvature of the functions to give you a better gradient, right? This gradient here we call the natural policy gradient, and this has many benefits. One of the particular benefits is to avoid this vanishing gradient issue, and then there are also other benefits too that I will discuss soon. So the folk norm, like empirical folk norm that was known in the literature, is really this helps you to encourage exploration. But there was not really a good understanding of exactly how this helps with the exploration in theory, and also how does this helps you ease the optimization. So in one of our results, maybe I just briefly mentioned the results here. First of all, in the existing work, what people shown very recently in the last year during pandemic is that if you consider the tabular setting, and then if you use this entropy regularization, then it will actually help you a lot with the convergence, both for policy gradient and natural policy gradient, right? If you don't use any entropy regularization, those are the rates that people have been shown that both policy gradient and natural policy gradient converges in the rate of 1/t to the true optimal policy, although your objective is non-convex, right? So if you use entropy regularization, you'll get linear convergence instead.
But not to the same thing, right?
But not to the same thing, yes. And if you, right, it's not to the same thing, and you need to like select this lambda appropriately to make sure that the solutions will be close to each other, right? So one interesting question that we try to understand is in the function approximation case, does this do we observe something similar? So what's known in the literature is that without entropy regularization, this problem using in the linear function approximation case is already much more challenging than the tabular setting, right? In the linear function approximation case, the best known result by Argava and all is to give you 1/√T complexity result. So what we've shown recently is that if you use entropy regularization, you can get a slightly faster convergence rate, 1/T, which is sort of not too surprising. What's kind of interesting is really that if we pose an additional like regularity condition, then we are able to also get linear convergence rate, right? So what do I mean specifically, right? So so this is kind of the main result. So first of all, it's based on two assumptions. The first assumption is this concentrability coefficient assumption, which is kind of very typical in most of reinforcement learning theoretical results, which basically says that you wanted to make sure that your policies at the initial point is kind of exploratory enough, right? So that this ratio here will be bounded, right? This is kind of a mild assumption that a lot of papers use. The additional regularity assumption that we make is to say that this parametric model at the initial policy is actually positive definite, right? This can be guaranteed if you use we've shown that actually this type of conditions can be shown to hold for the cases where the size of the dimensions is sufficiently large. So the number of feature vectors we use is sufficiently large, then we can show that this actually hold. So that's why we call it a very mild assumption here. And in terms of the result, we've shown that like after T number of iterations, you can show that it will converge with this linear rate, which is proportional to, of course, how you select this number. And then it will also subject to some approximation, like function approximation error, right? Because the true value functions is not necessarily, or the true policies is not necessarily always represented by this linear function approximation with softmax parameterization. So that is kind of the main result we shown. As I said, of course, the result is still kind of limited because so far we're requiring that we know how to compute exactly the gradient. And we do also have some recent results that showing if you don't really know the exact gradient, and we can also use sample-based methods to achieve similar bounds, but then there will be additional statistical errors too. Okay. And then I should also mention that you can easily combine this result with what I discussed before for policy evaluation. If you use neural function approximation, we can show something basically similar. If you replace, so here, instead of using this linear function approximation inside, if you use a 2-layer neural network or use general multiple layer neural network, we can use the similar tricks that I discussed in the previous part to derive basically similar results without loss of generalization. So I think it's time that I should conclude here. So basically I talked about the 3 kind of commonly used reinforcement learning tricks and kind of explained why they work and sometimes why they does not necessarily work in theory, and explain then what are the connections to optimization. Hopefully this is something that makes sense to you. And of course, as I said, there are many other tricks people use in practice besides these tricks, and the combination of many of these tricks is really what leads to the success of deep reinforcement learning. And there is clearly a long way to go to bridge this gap between theory and practice. And with that, I will just conclude here and thank you for your attention. Yeah.